All right, so it should be recording right about now. Cool. Okay. Okay. Maybe just give it a minute and then we'll start. All right. Okay. So I think now's a good time to get started. Cool. So hello, everyone. My name is Amar Khudr, and I'm the lead at the SCAUB. Our event today is one that has been months in the making and is rather fitting for the virtual format that we're adopting for now. Since our speaker is joining us all the way from the US, it's actually 8 a.m. his time right now, so apologies for the early time for you. So our speaker today is Peter Kairouz. So Peter is a research scientist at Google, where he leads research efforts on distributed privacy preserving and robust machine learning. So the session today is just about that. He's going to be telling you guys more details about that. But the general idea is that it's a recently conceived approach in machine learning called federated learning, which addresses many of the challenges researchers face today when it comes to training machine learning models on decentralized data. So that's data that's present on the devices we use daily, like smartphones, smartwatches, IoT devices, while at the same time making sure that user privacy is maintained, the user experience isn't hindered, and data consumption is minimal. So without any further ado, I'll be leaving the floor to Peter so he can tell you all about how him and his fellow researchers at Google made this all happen.
Yeah, thanks a lot, Ahmad. And hi, everyone. I'm Peter, and so yeah, I'm going to be talking about federated learning, but this is work of a lot of people at Google, and even some of it is developed beyond Google. There's a community of researchers. Hopefully, you're going to be members of this community after this talk. So let me get started, and I'd like to start with this slide because data is perhaps one of those things that combine a lot of computer scientists and engineers. We all work with data in a way form. And data is almost always born at the edge on our computers, smartphones, cars, smart home appliances, so on and so forth. And all these devices are generating thousands of gigabytes of data every single second. So there's this huge explosion in internet growth, in connectivity, and in data growth. And this data is actually very useful because we can use it to analyze metrics and trends, to come up with recommendations, to build machine learning models, to do analytics, data science, so on and so forth. And that's why we now have all these services that we absolutely like. But this data is also a little bit risky. It comes with a lot of sensitivity around privacy. And moving data around is actually very energy consuming. To move data back and forth between phones and computers and cars to servers, that consumes a ton of energy. And so the idea of federated learning was born from the question of, can the data be born and always remain on the edge? And if we manage to successfully resolve this question, we would be able to create a suite of AI and machine learning infrastructure and technologies such that you don't have to wait to get improvement of services from the service provider. It automatically improves on your device because it's trained on data that lives on your device. And we can save in battery. We can use even the models and the AI when there's no internet. And most importantly of all this, privacy is preserved because your data with all the sensitive information in it does not have to leave your device ever again. So this is the ambitious goal of federated learning. And one of the recent definitions of federated learning is as follows. It's a machine learning setting where multiple entities, we're going to refer to them in this talk as clients, and I'll elaborate on this notion of a client in a bit. They collaborate together in solving a machine learning problem. Now, in order for them to collaborate together, they have to do it under the coordination of a central service provider. Now, each client's data is never shared between the client and the server, or between the client and any other clients, any other participants. That data is always kept locally on the device. And only focused minimal updates are exchanged in the process between the client and the service provider. And these focused updates essentially strip off a lot of the sensitive information. And so we're going to unpack this statement over the next maybe 10 or 15 slides and tackle each phrase of it separately to see what we mean by collaboration, what do we mean by orchestration, how do we do all these things together. But this is, at a high level, the main definition of federated learning. And this is what we are trying to build at Google. All right, so there are different flavors of federated learning. It does not come in one and only one flavor. The one that we have focused on a lot in the past is called cross-device federated learning. And in this setting, the clients are devices. They are phones, laptops, computers, tablets, perhaps even IoT devices. So you can imagine you have perhaps millions or hundreds of millions or even billions of such devices. So we have a lot of clients here. But the amount of data per client is very small because each person will generate a little bit of data on their device. But collectively, there's a ton of data. And now the service provider can be a software company that's trying to build models for improved services. And it engages in this process of coordination back and forth between the server and the clients. And once the model is learned, it deploys it for use. And I'm going to unpack the slides later in this talk. But the other equally important and equally popular setting of federated learning is called the cross-silo federated learning. Silos are essentially containers of data that contain a lot of data that are and should be always separated. So here you have institutions. These institutions represent clients. For instance, you should think of a network of hospitals. Each hospital has patients, perhaps thousands or tens of thousands of patients, and medical records and patient data needs to be always separated. No two hospitals have the right to share data between each other. You can also think of a network of banks. You can think of a network of advertisement publishers. You can think of a network of schools. The same story repeats itself. There are institutions. Each institution has a lot of data. They want to train a combined model on the combined data between all these institutions, but they cannot share the data because of policies, because of regulations, because of privacy, and other things. Now, the stark difference between this setting and the other setting is that here you have far less clients. Usually you have tens, hundreds, or maybe even thousands of clients in this setting, but the clients here are much bigger and much more powerful. For instance, they're not computers, and they're not phones, and they're not IoT devices. These are institutions, so each institution can have its own cloud infrastructure, or it could have a bunch of servers. So compute power is not limited per client, and each client has possibly many thousands of training examples, or maybe even hundreds of thousands or millions of training examples. Whereas in the cross-device, you have far many more clients, but each client has far less compute power and far less data per node. Now, you may have seen in the classical setting of machine learning this terminology, cloud AI or distributed machine learning. And this is essentially a until today, one of the main ways of training models and AI in the cloud. So here, what I'm showing you on this slide is data that has been acquired by the service provider. And there's an engineer at the company that wants to build a model to improve a service. And so the way it's typically done is that the engineer would submit a request. The engineer would typically not be able to bring the data to their computer or to their machine and then do the machine learning on their computer. Rather, what happens is that the data is dispatched to servers. As you can see on the slides, I'm only showing you 4 servers. In practice, we can have tens or hundreds of servers. And then the computations happen on these servers. So any training or any AI people do is done on these servers. And all these servers actually live in the cloud. And of course, the engineer can inspect the data afterwards and inspect, the model to see whether or not it's a good quality model, can run some metrics, and then decides whether they want to stop the training process or continue or debug or do whatever they think is important for the process at hand. Now, because in this process, as you can see here, we are taking the data set and we are kind of sharding it into many pieces and submitting it as multiple jobs to multiple servers. A lot of people tend to think that distributed machine learning and federated learning are essentially the 2 equivalent paradigms of machine learning, but they are not, and there are some stark differences between them. There are some similarities in the sense that the job is not happening in one and only one place, it's happening over multiple servers, but there are also very stark differences. So this is a table that shows you some of these nuanced differences. And I would like to focus on a few of them. The one that I think is the most important one is the following. In the distributed machine learning setting, the one that I've just shown you on the previous slide, the data lives all in one place. You saw this container called cloud data. That's where the data lives. And so what you can do is, before you send it to a number of servers, you can take that massive data set and you can shuffle it. You can mix it up all together, shuffle all the records and all the rows of the database, and then shard it in equal partitions to all the servers that you have access to. Now, what this ensures is that each server is going to see a slice of the data set, and these different slices are not only of equal sizes, so the load is balanced, which is something that is very nice. We want the servers to be operating on equal loads and unbalanced loads, and not unbalanced loads. More importantly, these slices, they look very much alike. This shuffling and mixing process, when you take all the data and you just mix it together before you partition it and you shard it, this mixing process ensures that every server is going to see more or less the same statistics over the data, the same samples or the same demographics or the same labels, because everything has been mixed up all together. Whereas in the cross-silo or the cross-device settings of federated learning, this is not applicable. We would never be able to grab the data from all these clients, put it all in one place, shuffle it, and then repartition it. So it's important to keep in mind that in federated learning, these load imbalances, the fact that one client is going to have more data than the other, is going to happen. So we have to deal with it. Some clients are going to have maybe 1 training example or 10 training examples. Other clients might have hundreds or even thousands or tens of thousands. So the imbalance can be extreme between one client to the other. Another one is the fact that the way I use my keyboard or the way I use my YouTube app is perhaps very different from the way each one of you guys uses their keyboard. So we type very different, perhaps we speak different languages, and we write different transcriptions, we like different styles or movie genres. So this is important because we now need to develop algorithms that are able to tackle this non-IID nature of the data. Now, the other axis that I also think is important here is the scale of the problem. For instance, in distributed machine learning, we tend to have tens of servers, maybe hundreds of servers if the software company has a lot of compute power. Hundreds of servers operating in parallel to run a computation, to train a model. But for cross-device federated learning, we have potentially up to billions of clients. And that's, for instance, the number of people with Android phones or people with iPhones or even computers. Because of this mismatch in the scale, this gives rise to very different dynamics of how you should coordinate these things and how you should do the orchestration. Now, there's many more interesting differences. For instance, client statefulness, this is the second row on this slide, is an important one because in distributed machine learning and even in cross-silo machine learning, you can assume that each client or each server, if you want, they have a state. You compute something and you can, after you run the computation, you can store the results of the computation in a certain state on that client. And then when you revisit that client later on in the process, you can fetch that state and you can read what the output of the computation was, and you can resume the process using that result. This is unfortunately not possible in the cross-device because our phones have very limited memories and they run many apps and many services. We cannot just store the whole state of a training process and then later on in a few days come back to the phone, fetch the phone, grab the state, read the state. That's going to consume a ton of memory. Imagine we're training many models for many apps. It's just impossible to store it. We don't have the memory capabilities. We don't have the storage capabilities. So we need to think about stateless instead of stateful algorithms. And that introduces another layer of challenge. And communication bandwidth is another one. We cannot just ask our phones or IoT sensors to send arbitrary amounts of information. Internet bandwidth is important. We need to be mindful of what we exchange on the communication link between the server and the devices. So this is all to say that there are these very interesting nuances of differences between these settings. And it's important to understand the defining characteristics of federated learning. Now, for the rest of the talk, I will focus on the cross-device federated learning setting because that's the one that we have focused the most on. It does not at all mean that the cross-silo setting is not equally important or interesting, but because we know a lot about the setting, I'm going to try to tell you a bit more. Now, before I dive into cross-device federated learning, remember I told you that usually the way machine learning development is done in software companies is you have acquired data and you have this cloud data box that you can see here on this slide. The engineer in a team, think maybe YouTube, maybe Gmail, any team you can think of at any company would want to train a model to do some task of recommendation or some task of personalization. They would submit a job to the cloud and say, I want to train this model. This model has the following architecture, structure. I want to train it on this data for this many rounds. I want to use this optimizer. So all these things are hopefully things that you are aware of, you've seen before in the last session. And the way it's done is either in the cloud, the job is submitted to one big massive server and it's ran on that server using something like TensorFlow as a pipeline to train the model. Or as we talked before, you can have multiple servers in the cloud. You can have tens of them or even hundreds of them, and this job is ran in a distributed fashion to speed up the process. You can do it in lots of ways. And after you train, you get the results, you can compute metrics, and you can evaluate whether or not the model is of good quality. And if you think the model is of good quality, you can then deploy it to devices. So these are the devices here. You can think of these as laptops or smartphones or whatever, tablets. And so if the validation step is approved, what you can do is you can send the model to the devices. This is how we deploy models on devices. And then the model is on your device. It's perhaps a keyboard language model or some YouTube recommendation algorithm, whatever it is, it's used on your device. And that's pretty cool because people can get now recommendations and improved services. Now, what we are trying to do at Google is to try to replicate this process. We don't want the engineer to have to worry about how this process is done, but the main caveat between what I've just explained and what we are trying to do is that we don't have the data. Everything I just told you about in the last 3 slides was under the premise that the engineer has somehow acquired data in the cloud. And so there was this box of data in the cloud. But in practice, because of federated learning, we're never going to collect this data. But we don't want the engineer to have to worry about what am I going to do? How am I going to talk to these devices directly, grab some updates or models from them? It's a very complex process, and we want to hide it all under the hood and allow the engineer to continue to do what they would usually do without even noticing that under the hood, the entire infrastructure of machine learning has actually changed. So let me tell you how we do it. This is where federated learning is going to kick in. We don't have cloud data anymore, as you can see on this slide. So the training is going to be orchestrated back and forth between the server and the participating clients. All right, so this is an example of cross-device federated learning. There's a device, and now you can see that the data is actually on the device rather than on the cloud. And we usually put a number of criteria for devices to participate. For instance, we want to make sure that they are charging because we don't want to use people's batteries. In the training process, we always ensure that the device is plugged into the wall, so it's actually charging. We want to make sure that we are not consuming anybody's internet quota. So if you have 4 gigs of internet or 6 or 10 gigs of internet, we don't want to consume any of your internet quota. So we want to make sure that the device is connected to an unmetered network. This is possibly Wi-Fi or others. And we also want to make sure that you're not using your device because we don't want to mess with the experience of the user. So if you are using the device, if the device is not idle, then it's possible that if we do the training in the background, your phone is going to be slower than typical. So we make sure that the phone is idle. We make sure it's plugged in, it's charging. We make sure that it's connected to an unmetered network like Wi-Fi. And once you meet these criteria, there's a few others, then you are eligible to participate. So what your phone is going to do, it's going to ping our servers and it's going to say, hey, I'm available. I met all these criteria, and do you need me for any computation? And oftentimes, because we get a lot of requests on the order of billions of requests, that's, it's a large-scale system, the server responds saying, I don't need you, not now. Come back later. And every once in a while, the server responds to a number of devices, thousands of devices. I'll give you some metrics in a bit, and says, yes, I need you. I have a computation for you. And so once the server responds to the ping by saying, yes, I have a computation for you, that's when the actual training process starts for this device. So what happens here is that the engineer would start from an initial model. This is what I'm showing here as this green box on the slide. This initial model can be a pre-trained model on publicly available data sets, for instance, or data sets that the service provider has acquired in the past. So you start from an initial model. It could be even randomly initialized. It doesn't have to be a pre-trained model on any data. It could be just like randomly initialized model. So the engineer would send the model with its architecture and the computation that needs to be run to the device, and we're going to talk a bit more about what we mean by model architecture and computation. And then on the device would use a platform. We use TensorFlow Lite to compute on the data and update the model. So that yellowish box is the updated model. That's an improved model. You get an initial model, you compute on that initial model using the data that you have, the labels that you have, and then you get an improved model. This is the updated model. And then what happens is the server receives multiple such updates from multiple clients. And this is what I will be showing on the next slide. But one thing to ensure here is that these updates are ephemeral, meaning that the server is never going to store these updates or save them. It's going to use them to update the initial model, and once it has updated this initial model that I'm showing you on the slide, it deletes them right away. So we don't send the data back to the server, but even those updated models, we delete them right away after we aggregate them. So here's the picture. Let me show you. You have a number of devices or clients that have participated in this computation, and each one of them has sent an updated model. You can see here the yellow and the gray ones. These are the updates that are incoming from the devices that have participated in this computation. We aggregate them. I'll talk a bit about the aggregation step, the summation box that you see in the cloud. And then we get a combined model. And once we get the combined model, these updates are automatically deleted. We don't keep them, we don't store them, nothing. We don't access them. Now, this combined model is analyzed with metrics. We try to run some tests on it. If we feel that this combined model is of good quality, then we end the process. That's it, we're done. We did what we wanted to do, which is to get a good high quality model. But if we feel that we're not there yet, our metrics, our losses are still bad, then what we do is we run another round of this computation. So you can see here what happens is we take this combined model and then we pass it on to a new slice of clients in later rounds, and we do the same thing over and over again. So you can see, for instance, now we have yet another combined model from these newer updates in this other round of computation. And we can continue to repeat the process. I'll give you some metrics in a bit of how many times we need to do this until we converge, until we get a good high quality model that works well for everybody. And that's when the engineer would say, all right, stop the process. I want this model. And it takes the model, it does A/B testing on it, and then it deploys it. If you don't know A/B testing, that's fine. It's just a way to compare the technology that you currently use to the improved one in a smart way. All right, so these are the orders of magnitude that I would like to very much emphasize because these are very important. In practice, in our setting of interest, what we do is we usually have anywhere between 100 to 1,000 clients or users participating per round of computation. We're trying to push the envelope to tens of thousands. You can imagine that it takes a lot of infrastructure bandwidth and a lot of compute resources in order to be able to support tens of thousands of clients per round, because we have a lot of these computations happening in parallel at the same time for different engineers, for different teams and different tasks. And it takes us usually thousands of rounds to get to convergence. So we're talking possibly 5,000, maybe 8,000 or even more. And every round where you take an initial model and you pass it on to the clients compute the update, and they send back their updates and we aggregate them, this process end to end, it can take anywhere between a minute to 10 minutes. The reason why there's this big gap between 1 and 10 is because it depends on the model size. If the model is really small, it's going to take closer to a minute. If the model is actually quite big, it's going to take closer to 10 minutes, depending on the size of the model, depending on the complexity of the task. And we'll touch on this in a bit later. But what's important is if you do a bit of calculations from these metrics that I have on this slide, you can quickly tell that if I'm running for thousands of users and tens of thousands of rounds, and I have, say, 10 minutes per round, you can quickly deduce that this is not a process that takes an hour or two to finish. This is a process that takes a few days, even sometimes a few weeks to finish. So end to end, to get a high quality model trained with federated learning, we have to wait. And that's an important bottleneck that we have. We cannot do it faster because there's a lot that's involved here. There are these clients that they have to be available, they have to be satisfying the criteria we talked about. So there are so many things that have to happen here. All right, so now I want to tell you a bit about some of the algorithms we use. And what I've described on the previous slide was very general. I said we compute on the device, we aggregate on the cloud. There are these two things: computation on device, aggregation on the server. Let me make it a bit more specific. One of the algorithms that we've developed early on is called the Federated Averaging algorithm. And under this algorithm, the way we proceed is that on the device, we do a number of stochastic gradient descent steps. Now, stochastic gradient descent is an optimization algorithm. I believe Julia in the last session explained stochastic gradient descent to you folks. So hopefully you've seen stochastic gradient descent before. I don't have time to dig deep into stochastic gradient descent, but what I can say, it's a first order method to compute some optimal point of an optimization problem. And yeah, so SGD is something we use, but you can use something else. You don't have to necessarily use stochastic gradient descent. In fact, for those of you who know machine learning, you know that there are fancier optimization algorithms out there. For instance, there's something called ADAM, there's something called AdaGrad, and there are many, many other methods of optimization. So we don't have to necessarily use stochastic gradient descent. Even stochastic gradient descent itself, it comes with a learning rate, and so you can tune the learning rate to better converge or faster converge. So there are some hyperparameters here that are involved. There's basically the number of rounds that we have to do on the client, the size of the batch, the learning rate, the architecture of the model. All these are things that need to be determined, and they can be determined also on the fly, which makes this problem even more complex. Now, when we send these updates, we need to do an aggregation step on the server. The simplest thing we do is if we do a weighted average steps. Remember, I told you that each client will have a number of training examples, and one of the defining characteristics of federated learning is that different clients have different numbers of training examples. What we can do is, instead of just taking the plain average of the updates that are coming from the clients, what we can do is we can weight each one of the updates by the number of training examples that that user had. So say if I have 10 training examples and someone else has 100 training examples, I would get a weight of 10 divided by 110, and they would get a weight of 100 divided by 110. So because their model was trained on 100 examples, their model would get a higher weight. Because my model was trained on only 10 examples, my model would get a lower weight. So we can do this weighted average. And then we get the federated averaging algorithm. But you can do a lot of things. This is essentially, we've barely scratched the surface. This is something that we published on in 2017. You can imagine there's been 3 years. Things move really fast in this area. And so there are so many interesting questions that I would like to quickly go over, but not dig too deep into. For instance, one can ask, how can I make this process faster? So this is reducing wall clock training time. I told you it takes days to weeks to get a model. So it's important to try to reduce this from days to weeks to maybe hours, if possible. So how do we train in a faster fashion? And this entails developing improved algorithms, optimization algorithms, faster, more adaptive algorithms, perhaps even shrinking the sizes of the model so that the round, instead of it taking 10 minutes, it would take maybe closer to a minute. So you can think about all these strategies that engineers and researchers can use. Another example is this one on the bottom right corner of this slide, which is how do we expand the scope of federated learning? For instance, in machine learning, there's supervised, there's unsupervised machine learning, there's reinforcement learning, and lots of other interesting areas of learning. And for some of them, it's clear how we would do it in this federated setting. It's kind of intuitive how we would take the labels and how we would train and form the loss, so on and so forth. Julia has probably explained this stuff to you. But for other types of machine learning, for instance, unsupervised or semi-supervised machine learning, it's a little unclear how you can do it in a federated setting. This is because sometimes you don't have the labels to start, or the labels are actually on another device that you cannot access because of privacy purposes. Another one that I actually really like is this one here in the center. It's about debugging. What if the model that we're getting is bad? What if it's poor? What do we do? Classically, in traditional machine learning, well, you have access to the data set. You can grab the data set, see on which rows or examples of this data set the model is failing, and you can essentially inspect the data to see what's happening. Is the model the source of the error? Is the data the source of the error? Maybe I'm anticipating a certain encoding of the data or representation of the data, but I have something else. Or maybe the model itself has some kind of a bug in it. So debugging, any software engineer is equipped to know how to do it, and it's a very tedious process, as you probably may know. But what makes it even harder in the federated setting is that you cannot grab the data. If the model is failing, it is failing. You cannot go to the client and tell the client, give me your records, give me your training examples, take them one by one, feed them into the model, see why the model is failing, because that breaks privacy. That breaks the whole premise of federated learning. And so it's important to keep in mind that certain things that are relatively simpler in classical machine learning suddenly become really difficult in the set. And there are other questions. For instance, this top one here on the left is very interesting. How do we personalize these models? What I've just talked about in the session so far is all about training one model that works well for everybody. But it's impossible to get this one model that works well for everybody. Because as I said before, the way I type on my keyboard, or the way I browse the web, or the way I watch on YouTube is perhaps very different from each and every single one of you guys. And so it's important to come up with ways to try to personalize and fine-tune the model after this whole process is actually over. So these are all open questions in the space, and we have some answers to them. Another one is, how do we create algorithms and techniques that are robust to attacks and failures? For instance, some of these devices can be hacked. Some of you guys are in computer science, you've taken a hacking class, or you've hacked some devices. You can hack the data, so you can introduce poisoned data. You can infiltrate the phones and inject malicious data to the phones. And this malicious data can actually break the training process because it's bad data. So these updates that are coming from clients are bad updates. So they're going to basically poison the model that you're training. Or you can infiltrate the training process, which is even worse, because then you can do arbitrarily bad things. You can, instead of using stochastic gradient descent to minimize some loss, you can try to maximize the loss. So you can do something really bad for the model. You can start driving the model in very weird, crazy directions. And you can now have a loss that oscillates in some sense. And these attacks can be conducted both at training or at inference. Even after deployment, we have these inference time attacks. So how do we come up with a suite of defenses against these attacks? How do we put some knobs in order to make sure that compromised clients are not able to break the system? That's still one of the big remaining open questions in the space. We have some ideas, but we don't have full answers to these questions. Another one is one that I believe is very important, is fairness and bias. This is because, as I told you before, in every round we sample a number of clients, and we want to make sure that our sampling is representative not only of the majority of devices, but also of the minority of devices. We want to make sure that when we're training, we're including everybody in the training process. We're not only sampling from the US or from Canada. We're sampling from the Middle East. We're sampling from the Far East. We're sampling from India. So we want to make sure that the model we're getting is representative of the entire population and not just a sizable majority of the population. Even the data on people's devices can be biased. It can have missing labels or some imbalance of labels. Some people can only have one label, whereas the others can have another label. So it's a very rich set of questions of how do we deal with bias. All right, so these are questions. The last one is about privacy. Privacy is a big area of research under federated learning. In some sense, federated learning was born in part to resolve the privacy question. So one big area of research that's still open here is how do we provide stronger, more rigorous guarantees on the privacy front. So yeah, I mean, this could take on its own many hours of information to tell you what we can do on this front, but it still is an open problem. Now, if you would like to learn more about these areas of research, we've put up a paper on arXiv. I have the link on this slide. It's called Advances in Open Problems in Federated Learning. It has a lot of amazing researchers. It has 58 authors, so it's more like a mini book. It's written by people from 25 institutions, academics and Google researchers. And I have a picture of some of the folks that have participated on this slide. It's very well written, and it starts off as a very light kind of read, and then it gets deeper and deeper into some of these topics. So you can pick and choose what you want, what area you would like to get deeper into, but I encourage you to check out this one. It's a very nice manuscript on the current state of the art in federated learning and some of the remaining high impact open questions. All right, one thing I wanted to mention before I try to show you how we can do like a mini tutorial on federated learning, like how can we write it in code. Everything I talked about is about machine learning, but we don't have to only do AI and machine learning, we can do analytics. So the orchestration that I've described before, a server, client, there's data on the clients, we go back and forth, we compute something, we improve it, that all can happen for analytics. And what is analytics? It's the practice of applying data science methods to the analysis of raw data that is stored locally on users' devices. So it's like federated learning. It works by running these local computations over each of the device's data, and we only make aggregated results, and then we don't collect any of the data. And so I'll give you some examples of analytics tasks. You may be familiar with some, maybe not. For instance, what if we want to just build histograms? So this is something many engineers at Google want to do, like they want to collect metrics, histograms over metrics, or multidimensional histograms and distributions. What if you want to compute quantiles or percentiles? What if you want to find the popular elements, tiles that people are clicking on? These, like, what are the most popular apps that are used in a certain store or something? And if you are familiar with SQL, essentially what we are trying to create is a federated version of SQL. SQL, you kind of write these queries under the assumption that the data is all in one place, but now the data is decentralized and it's just everywhere on many people's devices or institutions. And so how do we provide our engineers with a federated version of SQL? That's also a very exciting area of research. So this is all to say that it's not just about machine learning or just about AI. It can include analytics and others. You can generalize this notion to even federated computations. So you can think of any possible computation you want to do, but instead of doing this computation on centralized data, you can do it on decentralized data. All right, I think this is a good point to stop and ask if you have questions. Does anyone have questions for me on the stuff that I've presented?
Let's see.
All right, so it looks like there are no questions, which is okay. But please do ask me anything you want. If there was anything that's not clear, if I went too fast over something, or there's something that is just didn't make sense to you. All right, one thing I would like to show you before I kick off this mini tutorial is one big application we have at Google. So together with the Gboard team, this is Google Keyboards. If you have an Android device, you must have used Google's keyboard. Even if you have iPhone, many people have installed the Google keyboard on their iPhones. It's a very smart keyboard. It has lots and lots of AI and machine learning under the hood that are powering it. Whenever you type the auto-completion of the word, the next word prediction, even some recommendations that we do in the background, so on and so forth, these are all done by language models. Of course, we don't have time to get into what are these language models. These are deep neural networks of the type of recursive neural networks, but we've been able to successfully train them with federated learning. And in fact, one surprising result that I want to emphasize is this figure here on the slide. As you can see, the green curve represents the performance that we got with federated learning, and the blue curve represents the baseline that was obtained before federated learning. Now, this will take a while for me to explain why federated learning is actually outperforming the centralized baseline. It's counterintuitive. People would expect to see these curves be flipped, because you would think intuitively there must be a cost for getting additional privacy, for getting all the advantages and the pros of federated learning. It turns out that because of federated learning, we can train closer to the data, and we can improve these models actually faster, and we can train on even more data, because now we're respecting the user privacy. We're never collecting, we're never storing the data. These updates are deleted, they're ephemeral. We're only showing the updates to the service, to the engineer in the company in aggregates. We only show these snapshots of the model as it starts converging. Because of that, we can train closer to the data and on more data, and then we get better quality. And as you can see in this figure, we get actually a significant improvement. We get 24% uptick in next word prediction accuracy. This is a huge deal at Google. And we get 10% more clicks because of this improved model. And this is, again, very big. This is for next word prediction model. There are other models also in Gboard. There's the emoji prediction model. There's the action prediction model. For instance, this is the model that basically suggests a GIF, sticker, or search query in the Google keyboard. There's basically how do we improve the dictionary of words? How do we discover these new trending words? And all these are essentially models that are trained in the background, and we train them with federated learning. And we've published a number of papers on all of them with our partners at Google and the Google Keyboard team. So I invite you to check them out if you have time. All right, so now in the last 10-ish minutes, I would like to tell you about this tool that we have developed. It's called TensorFlow Federated. And I'll try to do like a quick demo as much as possible. Let me tell you why we need TensorFlow Federated to begin with. So we quickly realized as we were developing federated learning at Google that we need a platform, a tool, not only for people at Google to be able to run federated learning easily and quickly and improve the state of the art, but we also thought we wanted to empower researchers. We wanted to empower engineers and developers and software engineers outside Google. At companies and schools, we want to give them the opportunity to be able to create new algorithms. A few slides ago, I told you about these interesting hard questions that we are still trying to resolve, improving accuracy, efficiency, improving fairness and bias, improving privacy, robustness to attacks, so on and so forth. And so we don't want to have every person redesign and reinvent the whole wheel every time they want to do something on the privacy or on the robustness or on the efficiency front. We want to give them a platform that already implements everything in a standardized fashion for them under the hood, and they could just plug in their updated algorithm. So you come up with an idea, you don't have to bother about the details of re-implementing the whole infrastructure of federated learning from scratch. You would just implement your idea in an infrastructure that's provided to you. So this is an open source project. It's on GitHub. It's also featured on TensorFlow. It's based on TensorFlow. And it serves as like a common foundation for federated computations. Keep in mind that federated computations, what we're calling is federated computation, includes federated learning, which was basically what I talked about in much of this talk. And it also includes federated analytics, which I touched on very briefly towards the end. But it could also include other forms of federated computations. Now, the toolbox, if you want, has a number of APIs, and I'm not going to be able to touch on these APIs, but there's something called the Federated Computation API. This is kind of a low-level API. It's only for serious kind of developers and engineers, people who dig very deep. It provides new abstractions like programming languages and execution models. How would I define what a computation really looks like? Orchestration schemes. How do I change and mess with the whole paradigm? This is very low level, and it's very detailed, and it takes people some time to understand the low-level API, which is this federated computation API. But for hopefully people like you, students at universities, or even interested engineers and practitioners that want to develop algorithms or test them out, the two APIs you will be using are the TFF Learning API, this one here in the middle, to implement FL algorithms, and also the TFF Simulation API, because this is the API that's going to allow you to simulate on data sets that we host in our toolbox. So we have a host of data sets. For now, we have 4 of them. They're somewhat big. We have the MNIST data set, we have the CFAR data set, we have the Stack Overflow data set, we have the Shakespeare data set. Those are the 4 data sets that we host in TensorFlow Federated. And because we have those data sets already packed and ready for you, you can run simulations and experiments on those data sets. You don't have to worry about, oh, where am I going to get data in order for me to try algorithms? And how am I going to partition the data on clients? So let's see quickly how we can do it. I'm going to switch to a Colab notebook in anticipation that we will not have a lot of time. I've actually written down everything. This Colab notebook is, again, an effort of many people at Google. I want to do a massive shout out to Emily Glanz on our team, who developed much of this notebook. And there are tutorials on YouTube that take you step by step into this notebook, this Python notebook. You can also find it on our website. You can find it both on the GitHub and also on the tensorflow.org/federated website. So if you want to access it after this talk and play with things, change things around, and hardcode a few things, you can do it. But just to show you very quickly a few things, you can, as you can see here, in terms of imports, there's not much that's hopefully new to you. I'm importing NumPy, collections, things that you would typically import. This is TensorFlow. We need TensorFlow because we are doing everything around TensorFlow. And this is TensorFlow Federated. This is essentially the import that you absolutely need in order to do federated learning. So we just import it as TFF. Okay, so TFF stands for TensorFlow Federated. And the hello world is just simply here. You do tff.federated_computation, and you give it a Lambda function with just basically as a string, hello world. When you execute this, you're going to see the hello world. So this is just to make sure that you've correctly imported our package, the TensorFlow Federated package. Now, here's where things get a little bit interesting. I told you about the simulation API. This API has a bunch of data sets. So what you can do is you can say tff.simulation to access the simulation API. And then you want data sets, so you do .datasets. And then you grab emNIST. emNIST is, you may have heard of the MNIST dataset, which is the dataset of digits. emNIST is actually the original dataset by NIST. It's the one where each person sat down and wrote these digits. So we have the digits actually separated by the person who wrote them. And that's really nice because now we can take the MNIST data set, partition it into users or clients, and then each client would be the author of a bunch of digits, a bunch of 1s, 0s, 2s, 4s, 9s, so on and so forth. So this is called emNIST, the emNIST data set. And we could just say, okay, I want the emnist data set. I told you we have 4 of them. So instead of emnist here, you can access Stack Overflow, you can access Shakespeare, you can access CFAR, and you just load the data. When you load the data, you get 2 things. You get a training set and you get a test set. So like anything in machine learning, hopefully Julia has touched on this, there's training and there's testing. And those are important for to make sure our algorithms are working and to do evaluation in a good way. All right, so you can see that we can take the training data set, emnist_train, we can grab the client IDs. You can see here that we have, for this data set, around 3,383, not around, precisely 3,383 clients. So this is a smallish data set. You can think of larger data sets. Stack Overflow is a massive one with hundreds of thousands of clients. So if you want something challenging, we have that for you. And if you actually look at, if you try to inspect the data set, the training data set, you'll see that it has images, 28 by 28 images. Those are the little images of the digits. And this is kind of what you would expect. Now, what I'm going to do is I'm going to try to access one user. This is the 0th user, or I'll take the data set and the string, grab client IDs, and grab the very first client ID. And we can use a very nice API that we have created for TFF datasets, which is create TF dataset for client. And what this API does is it gives you a TensorFlow dataset for that client. So I'm grabbing the first client in some sense here. So I take client IDs, give it 0, gives me the ID of the first client. I give that ID to this method here, and it gives me the dataset of the 0th client. And I can grab, now because this is a TF dataset, hopefully you've used TensorFlow before, you can grab an example. You can grab one example from this dataset, and you can plot it using matplotlib. So you can see here that it came out to be the digit 1 or something. It's not very clear what this digit is, but this is one of the digits that you see. Again, it's a 28 by 28, so you can see here this figure. All right, so you can do something a bit more advanced. You can try to take all the digits of a particular user. So this is just showing you here. What we are doing is we take 40 examples, 40 training examples of a user in this example data set. So we're plotting them next to each other. You can see here the digits written by this user. There's a lot of 0s and 1s. There's also 2s and 5s, so on and so forth. It's unclear whether this one here is a 7 or a 1. But these are the digits that are written by the same person. So you can see how I'm plotting them here. You can do something else, something a bit more complex. This code, what it's doing, again, it's pretty much using the create TF dataset from client. But now instead of grabbing data from one user, I'm going to take 6 of them. So see this I here goes from 0 to 5. So I'm going to grab 6 clients, the first 6 clients. I'll take their IDs, I'll create their data sets, and for each one of them, I will loop over the training examples of that user, and I will form a histogram for that user. And I want to show you the histograms over these 6 arbitrarily chosen clients. And this is important. This is what I was talking about before. You can see here that they don't have the same distribution over their labels. In MNIST, there are 10 digits, 0 through 9. So this histogram is showing you these 10 digits. The x-axis of the histogram is the digit index, digit 0, 1, 2, 3, 4, up to 10, or sorry, up to 9. And what I'm counting is the number of occurrences of these digits on each client. So you can see that, for instance, client 1 has a lot of 0 digits. Sorry, client 0 has a lot of digit 0, whereas client 2 here has fewer of them. You can see how the load is imbalanced. And in fact, if you sum the number of digits that each client has, you'll see that they don't have the same number of digits. This shows you how the data is actually imbalanced and not necessarily sliced exactly from the same distribution. Some people write some digits more than others. And you can continue to do this experiment. You can look at, for instance, the mean image per label. we take, for instance, for client 0 here, the average 0 and the average 1 and the average 2. You can plot them, and you can take the mean for client 1, and you'll see differences. You'll see differences in the way people write 4, or a difference in the way people write 5, so on and so forth. For instance, here, there's a lot of variation as to how this person writes 2. That's why the mean image of 2 is very fuzzy. So I'm going to skip this to get to the important part. So if you are familiar with TensorFlow datasets, you know that we can easily reshape these datasets for training. So what we can do is we can form an ordered dictionary. And for this ordered dictionary, we can reshape the image from a 28 by 28 tensor, and we flatten it out into a 784 single-dimensional kind of tensor. So we just make a vector of it. This is the first step in any machine learning process, to just like pre-process the batch. We take the data, which is images, we just flatten it out. So, and we can do it for, depending on the batch size. So what you're seeing here in pre-processed data set, we have a number of hyperparameters. How many epochs do you want to run on client? And what is the batch size, the shuffler, so on and so forth. So there are these hyperparameters that we kind of touched on during the talk. And this is an important piece of computation that we're going to do before we do the training. So what we're going to do here is we're going to grab a bunch of data, and we're going to just pre-process the data. So example data set is this data set of 6 clients that I took above, and I did the analysis on it by plotting and showing the histograms, and I'll just apply the pre-process function in order to get the pre-processed example data set. And then I'll form my batch from it using the tfnest function. All right, so one thing, I'm going to scroll down in the interest of time, and I want to show you something that is relevant for you. You must have seen Kairouz. I think Julia covered Kairouz last time. Kairouz is this very nice skin, if you want, on top of TensorFlow. It also sits on top of PyTorch, where you can actually just define models of interest for you. For this task, because it's a simple endless task, for instance, we can have this very simple 3-layer neural network. You can see that there's basically the input layer. It takes 784 flattened kind of tensors. And then I have one dense layer, and then I have a softmax layer. So hopefully these things are things that make sense to you. But for that, we're just using Kairouz. If you know Kairouz, you can create the model that you want. This is a very simple model, and it's going to do a good job for this task, which is digit classification on MList. So this function just creates a Kairouz model. And the one difference is when you use TensorFlow Federated, what you have to do is you have to take this Kairouz model and you have to wrap it in a TFF learning API. So that's why, notice what's happening here. We do TFF.learning from Kairouz model, and we feed it the Kairouz model. So here, I'm going to give it a Kairouz model that I've created using the method I just went over above. So this here gives me a Kairouz model. I will call it on this line to get my Kairouz model. And once I get my Kairouz model, I will feed it into the TensorFlow Federated Learning API, which is going to create a model for us from a Kairouz model. That's what it is. And you can choose what loss function you want. We're using the sparse categorical cross entropy. This is very popular. People use it all the time. But you can change it to other things. And you can also specify the metrics that you want. So this is hopefully nothing too difficult for you. It's just, how do I get a model that I can use in TensorFlow Federated? And the baseline here is that you just create a Kairouz model, as you would have done otherwise. And then you feed the Kairouz model into a simple API, which is this one, tff.learning.from Kairouz model. And that's it, you get it. Now, this is the real business here. And this is perhaps the most important line that we're going to see in this entire thing. We're almost done. How do I actually start the training process? And this is the power of TensorFlow Federated. In the learning API, so how do you access the learning API? You do tff.learning. This is the learning API. what we're going to do is we're going to build a federated averaging process. Remember, I talked about the federated averaging algorithm? And so this is essentially that to some extent. And we're going to build it using this method, build federated averaging process. What would it take? It takes three things, and those are hopefully going to be reasonable to you. It takes a model. In fact, it takes a model function, the function that's going to create the model. And this is what we've just done, which is basically we have the function that creates a Kairouz model, and we wrapped it with a TFF function that creates a TFF model. This is what we feed here, this model function. So this model function is nothing but this one, but we just went over it. And then there are two things. Tell me what you're going to do on the client, what optimization method you're going to use. And notice what I'm doing, again, from Kairouz. I'm grabbing an optimizer, which is a stochastic gradient descent optimizer. So I'm going to use stochastic gradient descent on the client with a learning rate of 0.02. You can change the learning rate to whatever you want. And you can change this optimizer. You don't have to use stochastic gradient descent. You can use Atom, you can use Adagrad, you can use your own fancy optimizer, plug it in here, and it will work. And also on the server side, remember we said what you can do is you can average these updates. Well, I'm going to use a stochastic gradient descent step on the server side because you can do all kinds and all sorts of things of weighted averages, and you can combine them with a learning rate, so on and so forth. You can go crazy, actually. You can do so many interesting things. And so for the sake of simplicity here, I'm going to do stochastic gradient descent on the server side, but I'm going to use a learning rate of 1. So I'm not going to change how I combine updates across rounds on the server. So you can see how easy it is. It's just the model, what happens on the client, what happens on the server. And with these three things, which are almost entirely based on Kairouz, if you know Kairouz, you can create these three things. All you have to do is just call tff.learning.build federated averaging process, and that's it. You get your iterative process, which you can now run. So you can now execute the simulation on your data set. So notice how we're going to do it. I'm going to skip these things here because they're not too interesting. Let's say I want to do some number of rounds. I have a simple Python for loop. For round num in range 2 to num rounds, I would just take this iterative process and do dot next. So I give it training data, and I give it the current state. This is capturing the model on the server, and I hit dot next. And it does a full round of taking that model from the server, putting it on the clients, computing SGD on the clients, taking the updates from the clients, bringing them back on the server, combining those with some optimization scheme, and updating the state. So notice, I give it a state, and it gives me a new state. State in, state out. And this new state has the model that you want, and there are also metrics. These are, we're tracking the loss in the training process. And you can do it for any number of rounds. In this case, I'm just doing it for 11 rounds. So this is 11 rounds of federated learning. And again, I ran this, you can see around 2, 3, 4, up to 10 here. And you can, if you notice here, this last column, you can see that we start with a loss of 2.88. We go down all the way to 2.12, which means that our loss is actually improving while we go through the training. So it's actually a good sign. If your loss does not improve, then there's a problem here. And we can also show the accuracy, and the accuracy, as you can see, goes from 0.15 all the way to 0.3. It also means that the accuracy, the categorical accuracy, is actually improving, which is a good thing in machine learning. You want the accuracy to go up, you want the loss to go down. Now, we can do more advanced stuff, but in the interest of time, I will stop here. Again, this notebook is available on our websites, GitHub and TensorFlow.org. I invite you to take a closer look at it. You can change a few things in it. It's easy to run it in Colab, in the notebook itself, because MNIST is somewhat a small data set, but if you want to move to larger data sets, you would have to do more advanced things. And if you have any questions, please do not hesitate to ask me now or later. Switch back to this.
So I actually had a question regarding the sort of security aspect and then
from my understanding, if you're gonna, when it comes to the orchestrator, sort of picking the devices to go into the round, so I'd assume they'd have to have the latest security updates. Does that create a discrepancy when it comes to making sure the sample is comprehensive? Because I'd assume many phones, that would be a challenge. Obviously, many devices potentially don't have latest updates, and that could cause a security threat, things like that. How do you handle that in the real world?
Yeah, that's actually a very nice question and a spot-on comment. You're absolutely right. If we want to make sure that we are defending against attacks, we want to make sure we are using the latest Android, latest security patch. And what that means is only people with the latest and greatest phones and latest Androids can participate. So you can imagine that it introduces bias in the process because people with older phones or older operating systems are not going to be included. And so what you are essentially alluding to is this tension between fairness, because we want the model to be representative and comprehensive and inclusive, but at the same time, there's security. We don't want to somehow break the model completely, and then we would not be serving anybody. And so there are ways around it, and I invite you to check the paper that we've put up on arXiv, Advances in Open Problems and Federated Learning, for how we can do it. But it remains an open question. So we don't have a clear answer to this question. For instance, one way, and this is a very naive strategy we can take, would be to run a federated learning training job on everybody without placing any restriction on the operating system. It has to be the latest with all the security patches and updates, and run another one only on the latest phones and the latest Android devices. And we take the two models and we compare them. If the two models are performing almost the same in some sense, then we only retain the one that was learned on everybody. It means we were not hacked, we were not compromised. So we can use the one that included people with the latest and without the latest Android. But if they are very different, it means that there is something. Now, how do you tell if this something is just because of very different demographics or because of an attack? That's where the question remains open.
So if anyone else has any questions, please leave them in the chat. I don't think you can turn on your mic unless I allow you to. So please, if you have any questions, please put them in the chat.
Yeah, it looks like there are 4 people who are able to speak. You can always reach out to me offline if you want. And all these resources are actually available on our GitHub and on our website. So hopefully you'll have easy access to them.
Great, awesome.
Thanks, Kairouz.
All right, so if there aren't any questions, I guess it's a good time to end the session here. Thank you so much, Peter, for the session. I'm sure we all learned a lot, and for Julia for introducing us to the main concepts. Massive shout out to her. That was a great session, by the way. So, yes. So thank you all so much for attending. If you guys have any questions, I'll make sure to leave all of the resources that Peter mentioned on our social platforms later on, if you guys want to check them out. And if you want to contact Peter, I'll make sure to get his contact information as well if you want to reach out to him personally, if you want to ask him any more questions. So, thank you guys so much, and have a good night. Take care.
Yeah, thanks everybody. Enjoy your night. All right, goodbye.